Today we are going to talk about the number E, which sounds like a strange thing to say because we always thought E was a letter, but E is actually a number as well. I always kind of feel like I'm on Sesame Street when I teach this lesson. It's like today's lesson is brought to you by the number E, which would have never been something they said because E would be the letter and they'd give you a different number. But today we're going to talk about E as being a number. This formula looks pretty overwhelming because of the notation, but the idea is that n in this formula is becoming bigger and bigger and bigger, heading off to infinity. So it's becoming huge. So what we could do is start by like plugging in 1. If I plug in a 1 for n, the calculator tells me that answer is 2. Okay, well if I'm heading to infinity, plugging in a 1, although a good place to start, is not even really very close. So I'm going to instead plug in 100. If I plug in 100 for n, I get 2.7048 and some more stuff. If I plug in 10,000, adding a couple more zeros onto this thing, because I'm letting n go to infinity, so get bigger and bigger and bigger and bigger and bigger, I get this number. The bigger I let n get, it's just going to keep on getting closer and closer and closer to this number. It's not going to keep getting bigger forever. It's just going to keep on getting closer to that number. The idea of an asymptote. It's just getting closer and closer and closer and closer to that number. That number is named E. It is named E because the man who discovered this number was named Euler, which is spelled E-U-L-E-R. So this is Euler's number, so we call it E. Yes?
How did they find that number if they can never do that number?
Like pi, E is an irrational number, so we don't know what all the digits are for it, but we know that it goes on forever, and we know that it never repeats. Same type of things that we know about pi. And just as pi is very useful, E is a very useful number. It has a lot of practical purposes. Since E is just a number, albeit kind of a mathy one, it behaves just like any other number or just like any variable, because a variable is just a letter that represents a number. So if I had x to the third, x to the fourth, what would I get? X to the seventh. So if I have e to the third, e to the fourth, I get e to the seventh. So our first few problems here are just going to remind us of our exponent properties. And the exponent properties hold for the number e because e is just a number. So we can divide the coefficients and get 2. And what is our division rule for exponents? Subtract them. So I get 2e to the first, or just 2e. What do we do when we have a power outside of a product? Power to a power will be a multiplication, and we need to give it to everything in that group. So I need to square the 3 and get 9. And power to a power, we do multiplication, so e to the negative 8x. What do we do with negative exponents? Do the reciprocal. So that 9 is fine. It doesn't have any negative exponents, but that e to the 8x needs to go down to the bottom of the fraction. So when our directions say simplify, your answer should be in terms of e. Just do our exponent properties that we learned earlier this year, applying them to the number e. The next question asks us to approximate on a calculator. Decimals are only appropriate as answers if the directions specifically tell you to approximate or estimate or go to 3 decimal places or something like that. Otherwise, if it just says simplify, leave e as e, like we did on those first questions. But here we're going to do this on the calculator. Your calculator has 2 different places to find the number e. the first place to find the number e is on the division button. If we press second division button, that will bring up an e. I have no idea why they chose to put it in two different places, two different places on the calculator, but they did. The other place we can find it is by typing second and this button that says ln, which is right next to the 4. I always use that one because it brings up e to the power of, and almost always we're going to be raising e to a power. So in this question, it asks us to find e squared, or e to the power of 2. So we'll type in our 2, close it out, and hit enter.
How many decimal places do you want to say?
The book says to go to 3. The next question also is an approximate on the calculator, and we want to do e to what power?
Negative 0.06.
And again, go to 3 decimal places. To graph with an e in it, we are going to do the same thing that we did before, making an XY chart. But before we look at graphing, one of the homework questions you're going to have is going to ask you whether our equation is an exponential growth or an exponential decay. So yesterday we talked about exponential decay. There were 2 different ways that an equation could be decay. What were those?
Greater than 1 or negative exponent.
Close. Base of less than 1 will be decay, or a negative exponent. Well, if e is our base, how big is e? 2 point something, right? So that's bigger than 1. So the only way that we can have a decay equation, if the e is our base, is to have a negative exponent. So is this equation a growth or a decay? A growth. Okay? So one group of your homework questions will give you an equation and say, is it a growth? Okay. If it has an e as a base, the only way it can be a decay is a negative exponent. So we're going to expect a growth on this one. We're going to create a chart, plugging in values for x as we did before. Now because we need plottable numbers, we're going to get decimal approximations. So we're going to plug these numbers into our calculator and find the decimal approximations. When you do so, make sure that you do 2 times e, and it'll give you power of with parentheses. Type in the number that's there times the number we're plugging in and close those parentheses so that whole thing is up in the exponent. Okay, we want all of that up in the exponent. And when we do that, we get 2e. The 0.75 times negative 1 gives about 0.9. And you don't need to be really specific on these because we're only finding these so that we can plot points. And we can't really plot anything more specific than 0.9. What always happens when we plug 0 in for our exponent? We get the front multiplier. So we don't have to type that one in the calculator. We'll just get 2. Then when I plug in a 1, I get about 4.2. And when I plug in a 2, I get about 9. And then we are going to plot these points. I'm not going to plot that last one. But I connect to form the curve, and we do see that this is a growth then, as we expected it to be. We are also asked for domain and range. What do you think about domain? All reals. Exponential growth or decay with any base will always have a domain of all reals. Range talks about y. Is it greater or less? Greater than what number? 0, because that's what horizontal asymptote is. we are only getting values above that flat line of 0. It's never going to touch 0, and it's never going to cross below. Questions? This one has some addition and subtraction, which is going to create shifts in our graph. What does that minus 2 do? And what does the plus 1 do? So we're going to go right 2 and up 1 to create our new center. And then when we make our chart, we do so only for the stuff we haven't already taken care of. So that leaves just e to the x. When I plug in a -1, e to the -1 is 0.4. E to the 0 is 1. Because any real number raised to the 0 power will be 1, other than 0. E to the first is just e, which is about what? About 2.7. And e squared we can type in the calculator and we get about 7.4. When we plot these, we do so from the shifted center. So from our new center, back 1, up almost a half. Over 0, up 1. Over 1, up 2.7. And connect those dots. Domain. All reals. Range. Y is greater or less? Greater because it's above. And what is it above? 1. Questions on graphing. The process is exactly the same as it has been for the past few days. The only difference is, to create our charts, we really have to use our calculator. Whereas I told you in the past couple lessons you were welcome to use your calculator to create your charts, today you really have to with that e in there. In lesson 1, we had this formula. What did that formula do? What kind of problem did we apply that formula to? Compounding interest, where n was the number of times we compounded interest a year. So again, to remind you how that works, what happens is you put money in the bank, and after some period of time, they give you some money, which we call interest. Then the next time they go to compute and give you interest, they do so not only off of the money you put in, but off of the money they gave you as well. So they're computing interest off of money that wasn't even yours in the first place. And we talked about in that lesson how the more often they do that, the better it is for you. So we said that they could do that annually, just once a year, or monthly, or quarterly, or daily, or all different options. And we said the more often it is, the better for you. Well, if we said they were calculating that interest every single moment of every single day, we would call that continuous compounding. Now, they're not always giving you that money. It's not like your bank account is just like changing. Like you can just sit there and numbers change. They still only give you the money at designated times, but they are actually constantly calculating the interest. And this is the way that most financial institutions do it, which is the best for you as an investor. However, the flip side is this is also the way that most credit institutions calculate interest, which means that if you are carrying interest on a credit card, you are going to end up paying interest on the interest. So that can become very painful. Instead of just paying interest on your purchases, you're also going to pay interest on your interest if you're carrying a balance on your credit card. But as an investment, this is a very good thing. If we let n head off to infinity, saying that they are constantly, every single moment of every single day, figuring interest, this formula simplifies down a whole lot to A equals PE to the power of RT. This formula needs to be memorized. I told you the other one did not, but this one is a whole lot cleaner, and it's more practical since this is really the way that most institutions will do it. We call it our PERT formula if we just read across the letters. P stands for principal, or your initial investment. E is our new number E. R is the rate, and T is the amount of time in years. And it has to be calculated in years. So in this question it says we deposit $1,000, that would be our principal, to an account that pays 8%, that would be our rate, and we talked about the other day how that's a little ridiculous. That's not actually going to happen. Interest, and it says it's continuous. So that's where we can use this formula as opposed to the old formula. What is the balance after 1 year? That would be the amount of time. So our formula is PE to the RT. We plug in what we know. 1,000 E to the 0.08 times 1. And again on your calculator, make sure you put parentheses around everything that's supposed to be up in that exponent. When we're working with 1, it doesn't really matter, but if that time changes to be more than 1, you will get different answers if you're not careful about making sure that all of that is up in your exponent. So when we plug that in, what do we get? $1,083.28. Remember, banks are nice enough to give you interest, but they are not nice enough to round up. Always go to 2 places when we're talking about money, because that's what money does. And if you happen to round up, I'm not going to say you're wrong. I don't care that much about a penny off. But in truth, financial institutions do not round up. Questions?
I did not get that. I got 1.73 something. Oh, you know what? I forgot the E. Never mind.
And in this one, same type of problem. We have our principal, our investment of $1,500, E to the rate 0.075 times time, which is 1 again. Let me plug that in. We get 1616.82. Now, let's think again about how exponential functions grow. So in a graph, an exponential function looks something like this. So when I think about investment, what does that mean? If this is our time and this is our money, what does that mean we should do with our investments? Let them sit for a long time. Because over the first couple years, it's growing, but it's not making that big of a difference. But at some point, we're going to hit a turn, and our money's going to take off. Okay? So the longer we let it sit there, it's going to hit this turn, and then that's how we can get a pretty nice retirement package. Okay? Likewise, on the other side, credit, pay it off immediately before it can get to that turn. Otherwise, you're going to pay a whole lot for that thing that you probably didn't even really need in the first place.
All right. So with that, for the interest in an account, can you put in more money into the same account?
If we start adding money, we need a formula for that. This formula applies if I just take some money and let it sit and don't touch it at all. If we're going to start putting more money into it, if we're doing the same amount of money, the same periods of time, so like if every month I'm adding $50, that's called an annuity, and there's a different formula for that. This idea is more like I just received an inheritance, and I'm just going to put it there and let it sit.
So these two forms are the same thing. A equals PERT. It's the same thing as 1 plus L around.
Yeah, the PERT formula is the same thing as that compounded interest formula. It's just that that N in the compounded interest formula means how many times a year are they doing it. So 365 would be daily, but they're doing it every second of every minute of every hour of every day. So it's that N is enormous. And that's where that E comes into it. So your homework tonight is from lesson 8.3.